All right, let's get right into it. Today, we're unpacking a genuinely fascinating paper called Beyond Fixed Representations. Have you ever wondered what the actual fundamental ceiling of modern artificial intelligence is? We see the headlines every single day about models getting bigger and faster, but there is an invisible barrier holding them back from true open-ended superintelligence. Today, using a brilliant framework laid out by researchers Yuan Cao and Hai-Chin Young, we're going to figure out exactly what that ceiling is, why it exists, and what it's actually going to take to build a machine that innovates just like a human.
Think about it. We've got this crazy paradox in modern tech right now. Current AI systems are mind-blowingly impressive. They can pass the bar exam, write incredibly complex code, solve advanced logic puzzles. But they can't invent an entirely new field of science. Why is that? Well, it's because modern AI is fundamentally built to solve predefined puzzles. You give it the rules, you give it the vocabulary, and sure, it'll find an answer. But it totally lacks the ability to invent new frameworks of thought. It just can't realize when the rules of the puzzle itself need to be rewritten.
To really wrap our heads around this, imagine dividing all problems into two distinct buckets. In the first bucket, we have intraspace search. These are type 1 problems. The vocabulary, the tools, the rules, they're all handed to the AI on a silver platter. It just searches within that existing box for an answer. And honestly, this is where modern AI absolutely crushes it. But in the second bucket, we have generative frame change. These are type 2 problems. This happens when you realize the box you're searching inside is actually broken or inadequate, and you need to invent entirely new concepts to change the frame itself. Current AI fails spectacularly at these type 2 problems because it just doesn't know how to rewrite the rules. So what exactly prevents our smartest models from making those open-ended discoveries? It basically comes down to two major innovation gaps. Here's the thing. Human progress isn't just about piling up more and more facts. The history of progress is actually a history of inventing new vocabularies. Think about when humans invented the concept of negative numbers. That wasn't just finding a new answer to an old equation, it was the creation of a brand new representational primitive. Before negative numbers, certain algebraic operations weren't literally impossible to express. But once we invented that new concept, the entire framework changed and suddenly impossible math became solvable. True progress requires expanding the vocabulary. And that brings us to the first massive hurdle, the vocabulary gap. Right now, AI simply inherits concepts from its training data. It is a master at shuffling around and recombining ideas that humans have already figured out. But it suffers from a total inability to autonomously invent and stabilize new representational primitives. Basically, if an AI has never been trained on the concept of a number and you show it 5 apples and 3 chairs, it's not going to just autonomously invent the abstract concept of number to compress that new observation. It just relies on what we've already fed it. But let's say, hypothetically, an AI does somehow invent a new concept. Then we hit the second hurdle, the verifier gap. How on earth does it know if that new concept is actually any good? In standard AI tasks, verification is instant, right? Code either runs or it crashes. But in real open-ended science, like drug discovery, validating a new idea might take 10 years of clinical trials. So the verifier gap is the immense difficulty of judging the value of a brand new idea when its full payoff is hidden deep in the future. The researchers bring up this fantastic phrase, the usefulness of the useless, and this hits the nail on the head regarding why standard AI optimizers fail. AI is designed to ruthlessly optimize for an immediate goal. If it randomly generates a new concept that doesn't instantly improve its score, it deletes it, it throws it out. But in human science, an idea might look completely useless for decades, just because the context where it becomes a game changer hasn't emerged yet. Current AI deletes these useless concepts way before their paradigm-shifting value can ever be realized. Okay, so if current AI can't do this, how does intelligence actually work? Well, human intelligence operates in this continuous loop that the paper calls cognitive discrepancy reduction. Step 1, you identify a mismatch, a gap between what you currently know and where you want to be. Step 2, you perform a cognitive transformation. This isn't just blind guessing, it's using operations like abstraction or analogy to actively change how you represent the problem. And then step 3, that transformation reduces the discrepancy. Intelligence is basically this relentless drive to find a gap in your knowledge, invent a new way to frame the problem so it fits, and close that gap. Now, we do have all these established frameworks for how AI thinks, whether it's based on finding the simplest explanation or minimizing free energy or mapping structures, and they're built on brilliant cognitive priors like simplicity and parsimony.
But if you look closely, there's a fatal flaw. None of them contain frame-changing operations. They're just isolated slices of cognition. Crucially, every single one of them is trapped inside fixed representation frames. They optimize perfectly inside the box, but they have no mechanism to break out of it.
Which leads us directly to how we measure this progress, the autonomy ladder. Let's climb this ladder really quick. Down at level 0, we have direct intraspace search. Think basic LLMs or RAG systems. You ask a question, it checks its fixed data, it spits out an answer. Level 1 adds a cool improvement loop. Systems like FunSearch generate candidates, test them against a fixed rule, and iterate. It's better, but still stuck in a fixed vocabulary. Now level 2 is where it gets super exciting. Scaffolded representation search, like Dreamcoder or the AI scientist. They can search across different local abstractions and actually propose hypotheses. Incredibly impressive. But there's a huge catch. They still completely rely on a human to supply the overarching domain, the literature, and the final test to see if it worked. And when you map out the entire AI industry right now, it's actually kind of startling. Despite all the massive hype, all the models grabbing headlines every week, whether it's an alpha system or a giant LLM, they heavily cluster down at the bottom of this autonomy ladder. They are severely constrained by fixed vocabularies and external, human-supplied verifiers. We've essentially built the world's most amazing search engines, but we haven't built autonomous inventors. But look at the space right at the top. Level 3, autonomous, open-ended invention. This is the holy grail. This is where a system detects its own gaps, invents its own new conceptual rules, and revises its own evaluators to judge those rules. And it is literally a ghost town. It's an entirely empty space. There is no current general AI system that clearly reaches this level. So the big question is, what are the actual pathways to get there? How do we build a level 3 system? Well, right now we train AI mostly on next token prediction. We reward it for successfully guessing the next word within its current fixed frame. But the researchers argue we have to completely shift our training objectives to representation revision. We need to explicitly reward an AI for recognizing, hey, my current vocabulary isn't good enough for this, and then successfully inventing a better, more compressed representation of the problem. We absolutely have to start rewarding systems for changing the frame itself, not just playing along within it. To pull this off, we need a completely new architectural pipeline. It looks like this. Step 1, the AI generates a new primitive, a brand new concept. Step 2, instead of just wiping its memory when the chat window closes, it actually stores that concept in a persistent memory bank. Step 3, because true verification might take years, it uses surrogate verifiers, clever, fast heuristics to estimate if this weird new idea is worth keeping around. And finally, step 4, as its vocabulary grows, it has to self-extend its evaluation. It has to invent brand new tests to validate its brand new concepts. So boiling it down to the concrete technical requirements for the engineers out there, first we need entirely new training data. Not just data showing the end result of human invention, but data that exposes the messy step-by-step trajectory of how a concept was invented. Second, we need persistent primitive stores to consolidate useful abstractions over time. Third, surrogate verifiers are absolutely crucial to survive the long delay in real-world feedback. And fourth, self-extending evaluators that grow and evolve right alongside the AI's expanding mind. And that brings us to the core thesis of this whole paper. The big takeaway I want you to remember from this: true progress, whether we're talking about humans or artificial intelligence, is not just accumulating facts inside a fixed box. It is the continual, dynamic transformation of the framework of thought itself. If we want machines to truly innovate, we literally have to teach them how to tear down the box and build a new one. Which leaves us with one massive, provocative question to ponder. If researchers actually pull this off and an AI finally reaches level 3 and escapes its fixed representation box, what entirely new frameworks of reality is it going to discover? What new negative numbers or theories of entropy will it invent that our human minds couldn't even begin to comprehend? That is the true promise and, honestly, the incredible mystery of open-ended AI. Thanks so much for exploring this with me.